Hi, and welcome to my tutorial about detecting room modes using the WaveCapture software. I will try to convince you to minimize the room modes. There are actually two strong reasons to minimize room resonances. Let's pick a measurement, select it and go to the RoomMode tabs. And here we see the result of the calculation in the WaveCapture software. Here we can see the frequency response. It's actually up to 250 Hz or 300 Hz. And you see some resonances here. This is made of a very big FFT, it's downsampled by 1 million point FFT. And here we see the spectrogram, so we can see how it looks like in time. And here is the calculated suggestion for filters to minimize these resonances. And you can see that it will ring about up to several seconds, but you see up to 250 milliseconds here. And if you apply these filters in your system, then you can see the result here. And according to my experience, it's enough if these red lines will be up to about 100 milliseconds, or the filter is around between notching filter about 5 to 10 dB. That will minimize the room modes. The second reason for minimizing the room mode is that you can often got a very bad signal to noise ratio in the subregion, so you will be unable to find your subs in your measurements, and therefore unable to make the alignment of the subs. You can see this in this graph. It's any time graph, and you see here a lot of ringing, so which continues all the way. And the problem is that when you make an FFT, we use a circle buffer. So this tail here will come in the front here, and smear out the measurement. Normally it should look like this. Here the room resonances are removed by filtering and so on. So you got the tail will fall off, and you have a clean measurement. I have seen this problem in many files which have been sent to me from users. And their problem have been that they have aligned their top systems to the room resonances instead of to the subs. To measure room resonances, you require a quite long impulse response, at least 4 seconds and so on. And one of the problems have been that many users use real-time transfer function, which only provide around 1 to 2 seconds. And therefore you got this aliasing problem. Therefore I recommend to do the room mode detection and apply the filters before you do any other measurement for equalization and delay alignment of the system. Here is some advice how to set up for room mode detection. There should be a preset here, acoustic and room mode, and it contains log sign sweep. That's absolutely the best method to detect the room resonances, because it goes through all frequencies. Noise measurement, MLS and so on have FFT bins which have not that resolution. Then we need to have a quite long impulse response. The rule of thumb is that the impulse response should be twice the length of the reverberation time. So this is 4 or 8 seconds we can choose between. We can use an accelerated sweep because we don't need a high frequency information. We can use a low pass shelving filter, but it's not necessary actually because we only measure the subs. And time windowing is not used in this case because we pick the impulse response in the algorithms before any windowing is present. So that's it. Then I recommend to make measurement in several positions, at least 3. In bigger rooms it should be maybe 9 or something like that. But the thing is that, as we shall see later in the theory about room modes, there are modes and nodes. So in some positions the resonances is cancelled out. So to be able to pick them all of them, it's necessary to make measurement in several positions. These multiple positions has to be calculated for room modes separately. In this case we have 3 positions. But if we use the average will even out the resonances going to have any room resonances at all to be detected. So we go back here, and the new method is that we should check the operate on buttons here, and then we right click in the frequency domain and analyze room modes. And here you can see the different measurement and the room resonances are calculated, and here is a suggestion for filters to apply to the system. And of course this will improve the signal to noise ratio. And you can see here that what happened with the ringing in the room. The result is that it will be eliminated. But you can also use this bar here, which determines the average level, and in that way it's possible to make more efficient filter, but on the other hand you will reduce the energy in the sub. So one way to make this compromise is to look at the resulting 3rd octave band energy, and in that way see how much filtering you need. You can edit these filters. You can see the effect of them by turning on and off like this, and you can see that, for example, this second filter doesn't do so much. Maybe it's harm more because it take away the last hertz in your sub. You're able to edit the parameters like this, and then check the effect of that. And you can save these filters to a file like this. One trick is to append these filters to the output tab. So we go here and right click and append the filters we have saved like this. And now these filters will be used for the stimulus equalization. So when we go to the capture tab, and then we see that this EQ button here is lighting up in blue, and if we press, then we use this filter in the output tab as a stimulus equalization. So either you can put this filter in your system DSP, or you can use this stimulus equalization, which is a little bit quicker. Well, let's spend a few minutes on theory of the room modes. Here we see a time graph of a measurement of a room, and we have the direct sound and the early reflection, and then this energy will drop down in reflections or reverberation, and when the level have dropped to 60 dB below the direct sound, we call that reverberation time. What happens if we have room resonances? Usually we have the same reverberation time over all frequencies, but when you have severe room resonances, you will see in the reverberation time graph that, let's say, below 200 Hz, this will rise. Here is a few examples of arenas. There you see actually the reverberation time around 1 second, and then it will rise at lower frequencies. It's quite big arenas here, so it's around 125 Hz. It will double the reverberation time. So in my opinion, there is no reverberation below this frequency. It's the only thing you see is the resonance from the room. There are no reflections because the room is too small for B reflections, and these resonances should be treated like resonances. So this is how the room modes is created. We talk about the most common one is the axial room modes, where is standing waves between walls and ceiling and floor. Then we have tangential, which is in the middle of the surface, and also oblique, which is more complicated. But for a rectangular room, that is quite easy to calculate which frequency this resonance will appear. It's a half wavelength, so the distance here and the harmonics will be like the measure of the room, the length, height, and width of the room. As you can see in this picture, the room resonances has a fundamental frequency and then have harmonics. For example, if you have a room which is quite large, so the fundamental is around 10 Hz, then you can expect that you have harmonics at 20, 40, and so on. You can see that in this formula. That is the number of harmonics here. We have included that calculation in the RoomMode tab. So if you check this, you have the expected room modes here and here. So if you change the measure of the room, you see that you increase, and you have the fundamental resonance here, and then you can increase the number of harmonics like this, and in that way it's maybe possible to identify the measure of the room, and then you can add the tangential and oblique modes to what they are a couple of dBs less. If we take this real measurement, and then we can adjust these bars so they agree with the measured resonances, maybe like this, and then the room can be a multiple of this measured length and width and so on, of course, because it's they can be harmonics of the fundamental room resonance. But please be sure that even if we can calculate these room modes in a rectangular room, it's not true that they will actually appear in the real room. It's only a guide where it maybe can be. So room resonances are a little bit tricky to calculate in theory. Let's summing up why it's so important to minimize the room resonances. First, of course, it's to ring out the room for improving the audio quality. Then it's to improve the signal-to-noise ratio when you measure the system, for example, for equalization and for delay alignment. Please have in mind that it's only the room resonances produced by the PA system you can filter out. If there is a backline or acoustical instruments, you have to treat such room resonances by mechanical means. One solution is to use Helmholtz resonator. It's very often used in studios and control room to take care of acoustical instruments and so on. You can read more about Helmholtz resonators and how to calculate it on Wikipedia. Thank you for watching, and I look forward to hear your comments.